guys, 4.8 is Newton's method. So it turns out this is the last application of derivatives. In 4.9, 4.9 is really looking ahead to integral calculus. So Newton's method will wrap it up for our applications, and it's a cool one. I like ending with this one. Sir Isaac Newton developed this method. It's a way to approximate the roots of a function. We don't really use that language so much anymore these days. When we say the roots of a function, we mean the zeros, like the x-intercepts. So you might think, okay, finding the zeros or the x-intercepts or the roots of a function. Turns out the applications are much, much bigger. If you can find the roots of a function, then you can also find solutions to things that you couldn't find otherwise. Again, here we recognize we won't be able to get these roots exactly, but it turns out we can approximate them very, very, very accurately using derivatives, tangent lines, that sort of thing. Okay. So we'll start off, sort of explore this with an example. So it turns out just to develop this method takes quite a bit of sort of background. So we'll start that here. Approximate the root of f of x equals x to the fifth plus x minus 1. So as you look at that, you think, if you wanted to find the root or if you want to find the zero, right, kind of the simplest way would be say, well, set it equal to 0 and solve. Good luck with that. You're not really going to get too far because of that x to the fifth. And so you might think, all right, what does maybe the graph look like? So that'll kind of give us an idea and a starting point for this method. So right there, we've kind of zoomed in on where the 0 occurs. We can see the way that function sort of moves through the x-axis. The 0 is kind of close to 1. It's somewhere between 0 and 1, a little bit closer to 1. Okay, well, how is this helpful? Again, like how does calculus, how do tangent lines, how can that help us to approximate where that 0 occurs? Here's what we can do. Think, you know what, looking at the graph, it's kind of near 1, right? So what if we found the tangent line that passes by the graph at x equals 1? So here's what that would look like. If we found the point at 1, that purple dot, and then we found the equation of the tangent line that goes through it, we get something like this. Okay, well, how is that helpful? Look at the 0 of the tangent line. Where does that tangent line pass through the x-axis? That's pretty close to the 0 of the function, right? And we can highlight it there. That will give us a pretty good approximation of that root of that 0. Okay, so we're going to go through the steps here. Here's our strategy. Find the 0 of the tangent line at x equals 1. Okay. So let me repeat the function again and our strategy. Find the 0 of the tangent line at x equals 1. Okay, so first thing we need to know is the equation of that tangent line. Here are all the steps for that. To find the equation of that tangent line, of course, we need a derivative, 5x to the fourth plus 1. We would plug 1 into that, giving us 6. That tells us the slope of the tangent line. We'd also need to know f of 1. So we know where that point occurs. Turns out f of 1 equals 1 as well here. And then we can use point slope form, y minus 1 equals 6 times x minus 1. And let's go ahead and solve that for y. So we get the equation of the tangent line. And I'm just going to leave it as 1 plus 6 times x minus 1. There's a reason for that. It's going to help us develop some formulas in our methods later. Okay, so we have the equation of the tangent line, but now we need to find the zero for that tangent line. So what are we going to do? We're going to set the equation of the tangent line equal to 0, and then solve that for x. So we've got 1 plus 6 times x minus 1 equals 0. Solving for x, I'll let you guys check my work. It turns out to be x equals 5/6. Hey, not bad. 5, 6, and we saw the graph a second ago. That's a pretty good approximation for the root of our function. Here's the thing. We can do better. Look at it this way. We recognize by the graph that x equals 1 was pretty close to where that root happened. It at least was the closest integer to where the root was. So this is almost like our first guess, just visually, of where it is. We know it's not exactly at 1, but it's pretty close. We go through these steps and we realize, hey, an x value that's even closer than 1 is at 5/6. What if we went through this same process over again, finding the 0 of the tangent line, but now we found the 0 of the tangent line at x equals 5/6? Okay, I'm going to explain graphically what that would be in a second, but kind of in the end, the point is, why stop with just doing this whole procedure once? For an even better approximation, find the 0 of the tangent line at our new x value, 5/6. Okay, what would that look like? Here's what we've done so far. I've kind of zoomed in just a little bit more on the graph, right? So we found that equation of that tangent line. We found that 0. This purple dot is at 5/6. Why not do the whole thing over again? Let's find the point on the function at 5/6, just above it, right? About right there. Let's find the tangent line there. And check this out. We've got this blue tangent line, and look at the 0 of that. It is super close to the actual 0 for the function. Wow, like every time we do this, we make leaps closer to approximating that. And then you might even say, well, if we found this 0, why stop there? Do the whole thing a third time. Find where, whatever this point is, find where it is on the function, draw another tangent line, and you're just getting closer and closer and closer every time you do it. It turns out every time you do this again, you get an even better approximation for where that 0 occurs. And there's no limit to how many you can do. You're always going to get more and more accurate. We'll just say you can do this as many times as is needed for whatever your purposes would be for finding where this root occurs. We call this an iterative process. We'd say the more iterations that we go through, more iterations will give better and better approximations. Okay. We're not going to actually compute the next tangent line at 5/6, right, with all of those steps. And certainly, we're not going to do more and more of these. Here's the thing. With an iterative process, with an iterative method, we need a really efficient approach, because we just can't keep finding the equations of tangent lines in the way that we've been doing and the way that we just did a moment ago. We need this to be like a really quick formula that we can apply over and over and over again to get these more and more accurate results. Okay, so what we're going to do at this point is say, kind of reflect on our example and think, okay, if we were to, come up with a formula, how would we do that? What would that look like? So I'm going to bring back our example, f of x equals x to the 5th plus x minus 1. And we started at x equals 1. we realized the formula, or I should say the equation for our tangent line for this was y equals 1 plus 6 times x minus 1. Now let's look at all of the different values in this equation of this tangent line. What was this 1? The 1 came from plugging our x value into the function. That was the y value for our x, and it happened to be 1 as well. What was the 6? The 6 was the derivative value at 1. And then we're multiplying by x minus the x value. Okay, so we got the function value, the derivative value, and then x minus that number. From there, we set it equal to 0, and we solved, and this one happened to give 5, 6. Okay, let's like generalize this. What if we wanted to do this for any f of x with starting value that we'll just call x1? Okay. Well, we need to find the equation of the tangent line, but if we follow that same thinking, we'd say, okay, for starting value is x1, then we need to begin with the function value at x1, right? Plus the derivative value at x1, and then we'd multiply by x minus x1, just following exactly the same guidelines. Okay, what would we do from that? Well, we'd set the equation of our tangent line equal to 0. All right. Then we would solve for x. So if we're solving for this x here, what would that look like in general? We would subtract the f of x minus 1. We then need to divide by f prime x1. Finally, we would need to add the x1. Here's what it would look like in the end. Again, we would subtract the fx1, we divide by f prime x1, and then we would add, we could put it in the front, x1 to both sides, and we'd have this. Now notice I'm calling it x2 because that's like our second approximation. So we have a starting, like our first guess, and then we have our first approximation, then we have our second approximation based on that first approximation. Then we said, hey, why should we stop there? Why can't we get a third approximation? Okay, with this, we have the formula already. If we were to do a third approximation, we would be doing all the same thing again, but plugging in x2 instead of x1. So we can just go directly to the result and say our third approximation, x3, would equal x2 minus f of x2 over f prime x2. We wouldn't have to stop there. We could do a fourth and a fifth and a sixth, however many we deem necessary, right? So our fourth approximation would use x3 and so on. Oh man, pretty sweet. Now, even more like, so this was really good, right? Back in the old days where they could just plug these numbers in. Even for us today, it'll be even faster because we can use the recall features in our calculator and we'll be able to do these calculations super, super fast. Okay, we'll get to an example. We'll do that in a second. Finally, with this in mind, we can lay out Newton's method. We've done the theory. Here it is. Newton's method for approximating roots. You got to start with x1. Either x1 will be given to us, like we'll be told what to take as x1, or we'll need to choose it graphically. So we'll see examples of choosing it, how to choose it graphically. And it turns out there's a little bit more to choosing it graphically. There's some other things to be aware of. Obviously we'll get there when we get there. In any case, we need to figure out an x1. Once we have x1, then to find x2, boom, it's x1 minus f of x1 over f prime x1. And we can go further to get x3 and so on. Once again, more iterations will give increasingly accurate approximations. Okay, it's time for an example. We're actually going to bring back that same function, but now we're going to see how this works with Newton's method, with this iterative process, and with our calculators. Okay, we're going to find x3 for f of x equals x to the fifth plus x minus 1 with our starting value x1 equals 1. Here we go. Find x3 for f of x equals x to the fifth plus x minus 1 and x1 equals 1. All right. First thing we need the derivative, f prime x. 5x to the fourth plus 1. No problem. Wonder if I can get just a little bit more light in here. Maybe that'll make it a little better. Okay, a little bit better. We're going to recognize, right, x2. Let me just copy this formula. It's x1 minus f of x1 over f prime x1, right? The original over the derivative is how that works. We know what those are. Again, I'm just going to write this out with x1. Then I'm going to let my calculator do the hard work plugging in. x1 minus, how would this work? It would be x1 to the fifth plus x1 minus 1 over 5x1 to the fourth plus 1, right? My original function, my derivative. Why am I writing it out this way? Okay, grab your calculator. If you have a calculator similar to mine, a TI, it's probably going to be similar as far as what I'm typing in. Any scientific calculator should be able to do what you're about to see. Here's what we're going to do. Starting with our first approximation, we're going to type in that number, just the 1, and then hit enter. Why are we doing this? So if I type in 1, enter, well, it's just 1, but this is saving it in my calculator's memory. Okay, then I'm going to be able to recall it. Then to find x2, I'm going to use the answer feature of my calculator wherever I see x1. So I'm going to say answer minus answer to the fifth plus answer minus 1 over 5 answer to the fourth plus 1. And in my calculator, right, I'll need parentheses around that numerator and denominator. Okay, let's try it out. I'm going to try and keep that on the screen. Can I get it all? Maybe, maybe not. Okay, so I'm going to say my answer feature is down here next to enter on this. So I'm going to go second answer minus parentheses answer to the fifth plus the answer minus 1 parentheses divided by parentheses 5 answer to the fourth plus 1 parentheses. And now when I hit enter, it should be recalling the 1 in for all the answers, and that will give me x2. Okay, 0.8 and a bunch of 3s. Turns out that is the 5/6 as a decimal. I'm going to go ahead and record it as a decimal. How many 3s are there? 1, 2, 3, 4, 5, 6, 7. It gives me 8 3s. 1, 2, 3, 4, 5, 6, 7, 8. I'm going to record. Let's note this. Record all decimals that your calculator provides. We like decimals. A lot of times, we usually prefer precise answers like 5, 6. In this section, we like decimals because we're getting approximations. So I'm going to write down every value I see in the calculator. Okay, now I'm going to be able to very quickly find x3. How am I going to do that? Okay, so I still have this. What I can do, my little arrow button, I can go back up and highlight that previous line there, hit enter, and it will repeat it. But now this time, it's going to put in this 0.83333 in for all of the answers. So it's taking my x2 and putting it into that same formula. And if I just hit enter one more time, boom, I got it. There's x3, 0.7643821116, just like that. And I'm going to record everything here, 0.7643821116. There we go. Here, I didn't mention if we were going to do any rounding, so I'll just keep all the decimal places that I saw. That is nifty. Hey, what if, we got our answer x3. What if we wanted x4? How would we do it? Again, I could go up, up, highlight that. Now it's going to recall my x3. There's x4. And notice, right, each time it gets a little bit more accurate. And it makes these big leaps, right, every time. If I wanted x5, why not? You could just do that. And there you go. Do as many times as you like. Pretty amazing. All right, you guys. We're going to stop this video here. We've got a couple of more examples taking this idea just a little bit further than finding roots coming up.